Hello class. So today we're going to do 11.9, a representation of functions as power series. It's pretty interesting that everything that we do in mathematics can be written as a power series. Little did you know, right? But the one that we're going to start off with is this one here, where we have 1 over the quantity 1 minus x. It generates this series here. And this is it in summation form when x is less, the absolute value of x is less than 1 for the convergence. And so let's use an example of this guy and see if we can generate something that is going to be useful for us. So let's do this. So instead of using, we have 1 plus x. So I'm going to change that just a little bit. I'm going to change it to 1 minus a negative x squared. So now we have this in the form of that 1 minus x, where our x is going to be negative x squared. So when we write it as a summation, what's going to happen is I'm going to have n going from 0 to infinity. And then my x, remember, was a negative x squared to the n. But we can rewrite that so it's a little bit more helpful for us. We can say negative 1 to the n, right? Because the exponent will go to the negative 1. And then we can say x to the 2n. And this is our summation. And so what's going to end up happening here is we see that the signs are going to change. But instead of having x squared, x to the third, it's going to be doubled. So what we're going to end up having is 1 minus x squared plus x to the fourth minus x to the 6th plus, x to the 8th minus, and then dot, 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 going on forever. Well, what we end up noticing here is this is a geometric series, just like the original power series that we had. So since it's a geometric series, what do we know? Don't we know that they converge when negative x squared is less than 1? So what that is basically x squared is less than 1, or when the absolute value of x is less than 1. So the interval for this problem's convergence, the interval of convergence is going to be from negative 1 to 1. All right, so it ends up having the same convergence as the original function. And then we're going to be using this same strategy to manipulate problems as we go. Okay, so remember this well, this whole thing here. Okay, so again, we'll do another example doing the same thing. We want it written so that it's, remember, 1 minus x. So I'm going to rewrite this as 1 over 2 plus x. But then I'm going to rewrite that as 1 over 2, 1 plus x over 2. And then from there, I'm going to manipulate that just a little bit further. I'm going to go 1 over 2, 1 minus a negative x over 2. So now that we're in that form of 1 over 1 minus x. So then this can be written as the 1/2 can come out front. We have our summation going from 0 to infinity of our x now, which is this, to the n. Well, we can clean that up and we can get 1/2 summation to infinity from 0 to infinity of negative 1 to the n over 2 to the n. In fact, we can even, well, I'll do it this way, 2 to the n, and then x to the n. I can clean that up just a little bit more so that I don't have the constant multiplier out front since it's already there. I'm just going to make this 2n plus 1, x to the n. Now what happens here is, again, this follows that format that we had, and since it follows that format, we know that this is going to converge when negative x over 2 is less than 1. Or we can say absolute value of x is less than 2, right, by multiplying by the 2. And so the interval of the interval of convergence is from -2 to 2. Pretty sweet, right? Being a geometric series makes it very, very doable, very, very much something that we can handle. And it's just algebraic manipulation. It isn't a bunch of fancy calculus. All right, let's do one more example. So in this example, we're going to have to play with it a little bit. And so in order to be able to have a series that is something that we can manage, I'm going to go x to the third times 1 over x plus 2. That's the same thing, right? But then I can manipulate that to be x to the third summation of n to from 0 to infinity of, I'm going to get -1 to the n over 2n plus 1 x to the n. And so basically what I did is it ends up being the same thing as the one above, right? It looks identical because this piece is this previous example. I just pulled the x to the third out so that I could clean it up. All the work for this piece here is done in this example up here. Okay, now we have an x to the third out front and we can't neglect it, so we're going to have to put that in. So I'm going to get -1 to the n over 2 to the n plus 1, but now it's going to be x to the n plus 3 because that power rule adds the 3 to it. So we can see in this problem something pretty cool. What ends up happening here is it's the exact same problem. The x to the cube piece really isn't going to affect anything too much, and we can see we can even generate it. So when x is 0, we're going to get 1/2 x cubed minus 1/4 x to the 4th plus 1/8 x to the 5th minus 1/16 x to the 6th, and so forth and so on. And the interval of convergence of this one, since nothing has been changed, convergence is again from -2 to 2. So you can see in this example, by being able to see that I could go 1 over the x plus 2, I could generate this power and then bring that in and see that we can generate what the power series is. But not only that, we could even find the interval of convergence because we had one we already knew. So you can tell everything that we're doing in these sections now is based off of prior knowledge and understanding of that prior knowledge. So absorbing that information and having reference to it a lot is going to be very, very beneficial as you go through this. Now, there is going to be some calculus, right? We needed to do some calculus, and here's what's going to happen with that. So the power series, when it has a radius of convergence that's bigger than 0, if we're given this as our power series, it's going to be differentiable on that interval, right, from the center of the power series plus or minus the radius of convergence, right, because we want to be convergent. That's what we want to do. And then here's what we can determine. In that interval, we can take the derivative and we can take the integral. And what's cool about it is the radius of convergence for both of these is still going to be that same r. So whether we take the derivative or the integral, the radius of convergence will be the same. So I'm going to use this theorem in the next couple of problems so that you can see it and you can see how we use calculus to reason our way through these solutions. So here we go. All right, so in this example, they're saying to express 1 over the quantity 1 minus x squared as a power series by differentiating 1 over 1 minus x. But we know that the radius for this one already is r is equal to 1, right? We've done it in previous sections, and so we know that the radius is equal to 1. Now I'm going to generate it again for you just so you can recall. It's 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus ... And then that's going to be equal to this guy, right? With that radius of convergence of 1. And I gave it to you at the beginning of the class. Now, if we take the derivative, right? If we take the derivative of this, something cool happens. The derivative on the left, isn't that going to be... well, let's just do it this way. We're going to take the derivative and see what happens. So if I take the derivative of everything on the right? So if I go 1 over 1 minus x and take its derivative, aren't I going to get 0 plus 1 plus 2x plus 3x squared plus I'd get 4x cubed plus ... right? And what ends up happening is we're going to get that to be equal to n to the xn minus 1. And notice that we shifted 1 because now our count, we're not going to worry about this guy. He's actually going to get dropped. So this will be our first term. So we're starting at 1, then 2, then 3, then 4, then 5. In this one, we started at 0. That was our 0. Then 1, then 2, then 3, then 4. But here, because this is a 0, it's going to be dropped. So we're always going to start at 1. So in order to be able to generate our problem, what we're going to get is 1 over 1 minus x, that quantity squared, is going to be equal to, and we can shift over 1, I'll show you. We're going to get n to be 0, but since n is 0, that means we added 1 to everything. So I'm going to get n plus 1, x to the n minus 1 plus 1 is just going to give me n. And this is the summation form for this function. All right? It's pretty cool. Now this, if we go back to the rules that we had, we can see it tells us that it's going to have the same radius of convergence, as the original. And so our original before the derivative was 1. So then by theorem 2, by theorem 2, the radius of convergence is r equals 1, right? Even though we took the derivative, the radius is going to be the same as the original function, and that was r equals 1. Okay, so that's just the way you do it, right? So they're telling us to take the derivative, write it out as a power series, take the derivative of each individual. That's going to generate a new series, and we're able to get our new problem. Okay, and you can see even over here by the power series, right? It was x to the n would come down, and we get n minus 1, and we can see that that's there. If we were to take the derivative of this, we'd end up here, which is exactly what we're trying to do. All right, let's look at our next example. And here it's giving us a power series, right, for ln of 1 plus x, and we want to find the radius of convergence. Well, we know that 1 over 1 plus x is equal to 1 over 1 minus a negative x, which would give us 1 minus x plus x squared minus x cubed plus x to the 4th, ... And that would have a convergence of when it's less than 0. Well, something interesting here is if I have ln of x, right, ln of 1 plus x, isn't that equal to the integral of 1 over 1 plus x dx? Right? The antiderivative of 1 over 1 plus x is going to give us 1 plus x. And so what ends up happening there is we're generating our function. But the way I was able to manipulate it was I was able to write it as a power series in a way that I knew so that I could find the radius of convergence. And now what I'm going to do is I'm going to take the power series and integrate it as a bunch of individuals. Right? And so I should get that 1 becomes an x, that's going to become x squared over 2, then x cubed over 3, and x to the 4th over 4, plus x to the 5th over 5, minus plus some c, right? Now, because we're taking the integral and it's indefinite, we need to have this plus c piece. And so what we're going to have here is we're going to, again, first term of negative 1 to the n minus 1, x to the n over n plus some constant c, and we know that the radius of convergence is going to be less than 1. Now, if we know that we can find that c for a specific case, so if we put x equals 0 in, we're going to get ln of 1 plus 0 is equal to c, right? And so ln of 1 is c, but ln of 1 is 0. So c is equal to 0. So the result is we get a function that's negative 1 to the n minus 1 x to the n over n with that radius of convergence of less than 1. And so we know that r is going to be 1 again, just like we had before, right? Because again, it's a geometric series and we can see that r is equal to 1, and that's our solution right there. Pretty cool stuff. But again, all of this is understanding and seeing manipulation. So in this next example, right, it says, let's find the power series for tangent inverse. Well, tangent inverse we don't know anything about, but we do know that the derivative of tangent inverse is going to be 1 plus 1 plus x squared. And it looks like it's one that we may have played with before, right? Did we play with that one already? Yeah, we did, which is cool. So what ends up happening here is we get, all right, tan inverse of x is equal to the integral of 1 over 1 plus x squared dx. But we already know that one from the previous example. That was up right here. And so it's going to be 1 minus x squared plus x to the 4th minus x to the 6th, right? So we can generate that one. And we're going to get 1 minus x squared plus x to the 4th minus x to the 6th plus ... dx. So you can see once you start to have these ones that are relatively popular, you should write those down and have a reference sheet to be able to get to the power series quickly, so that you can generate and manipulate from there. You'll see in some of the homework, it'll be kind of like this example over here with the x to the 3rd that we did, where I manipulated so that I got to something I know and then brought it back in. That's going to happen quite a bit in the homework. So just be ready for that. So again, we individually integrate here. So we're going to get x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot 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 plus some constant c, right? Now, one of the things that's important in this case is we need to find for that c value, and again, to find that c value, let's plug in something that's going to make life easy for us. If we plug in x is equal to 0, we see that everything is going to be 0 except for c, and so when x is equal to 0, we're going to get tangent inverse of 0 is equal to this 0 plus c. So then that tells me that c is equal to 0, right? Because tan inverse of 0 is 0. And so the result is tan inverse of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot 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 dot, which we can write as a sum n equals 0 of negative 1 to the n of x to the 2n plus 1 over 2n plus 1 with a radius of convergence of 1. Pretty cool stuff. It's weird that we used the geometric series at the beginning, then manipulating that gave us this power function. That power function then integrated gives us the tangent inverse, and we end up seeing that tangent inverse is this infinitely long power series, which is pretty cool. In one of the homeworks or examples that I'm going to do for you, you're going to see that I'm going to take the power series for sine, and then I'm going to take the derivative of it, and it's going to give me cosine. And it's going to give me cosine in the power series form. So you're going to see that they are, in fact, interchangeable for each other. It's pretty cool. Well, I hope this was helpful. Study hard, start writing down these series and try to jot them down so you have quick reference. Again, during class, just be prepared to ask questions so that I can demonstrate these examples for you. All right? All the best.